In this video, we will briefly review X-ray beam terminology. We will contrast primary and secondary radiation barriers. We will then construct a radiography room to meet current regulations and discover the significance of controlled and uncontrolled areas within the medical imaging department. We will then explain equipment regulations including fluoroscopy and general radiography system equipment. To start, we will quickly review some basic terminology. In a radiography imaging system, the source of radiation is the X-ray tube. The primary X-ray beam exits the tube and interacts with the patient or body part that is being imaged. Only 1% of the primary X-ray beam passes through the part. The other 99% or so of the X-ray photons are scattered or absorbed within the patient. The photons that make it through the part being X-rayed are now termed the remnant beam. The remnant X-ray beam is what interacts with the image receptor to create the radiographic image. Through this process, we know that scatter radiation poses the largest quantity of occupational dose. In previous videos, we discussed scatter as a result of the X-rays interacting with the patient's tissues. You should know that scatter also occurs when the X-ray interacts with the table and other nearby devices. Besides scatter radiation, there are other factors contributing to occupational and patient dose. Leakage radiation is that which exits the X-ray tube housing and is not part of the primary beam. Leakage radiation is able to be diminished through equipment design. We will discuss that later in this video. Radiation from the primary beam, scatter radiation, or leakage radiation must be blocked to avoid exposing the general population and technologists. Imaging rooms that house radiation-producing equipment must meet certain requirements to make the environment safe for everyone. Structural barriers, such as walls, floors, and ceilings, are categorized into two types of shielding barriers, primary and secondary. Primary barriers are those which the primary X-ray beam is capable to strike. Secondary barriers are those that secondary or scatter and leakage radiation will likely strike, and primary radiation is not capable or permitted to strike. Primary barriers must have a lead equivalent thickness of at least 1.5 millimeters or 1/16 of an inch. Examples of barriers that require this type of protection include walls and the floor that the tube is able to be directed at. Such is the case for the wall behind the upright bucky and walls that may be behind a decubitus exposure. Secondary radiation is that which is scatter radiation or leakage radiation. This type of radiation requires secondary barrier protection that requires at least 0.8 millimeters or 1/32 of an inch of lead equivalent protection. Examples of secondary barriers include the ceiling and the wall of the control area. You should know that it is never acceptable to direct the primary X-ray beam in the direction of the area which houses the control panel. In the construction of this radiography room, we will identify the primary and secondary barriers and discuss the methods for creating a safe environment for technologists and those walking and waiting in the areas just outside the radiography rooms. As you can tell from this drawing, we have a wall already designated where the upright bucky will be. We also have a wall for the control area where the control panel will be housed. Which one is the primary barrier and which is the secondary barrier? Hopefully, you were able to identify the wall where the upright bucky will be housed as the primary barrier and the control area wall as the secondary barrier. The wall where the upright bucky will be located is required to have a barrier that meets the lead equivalent of 1.5 millimeters. Typically, the lead is attached to a structurally supportive substance to ensure that it stays in place and doesn't collapse under the weight. In our room, we will attach it to sheetrock. We will adhere this to the support studs, but only up to 7 feet, as the primary X-ray beam is not able to reach above this height in regular applications. Regular drywall or sheetrock can be used in the area above the 7-foot mark and behind other barriers. Next, let's review what is required for a secondary barrier of the control area wall. Again, we will adhere the lead to the sheetrock, but this time it doesn't have to be as thick. It only needs to be half of what the primary barrier was. so 0.8 millimeters or 1/32 of an inch of lead equivalent is required for this wall. You may notice that it does not have to extend above 7 feet. This area above the 7-foot mark can be left open and not reach the ceiling. The window in this wall that allows us to monitor our patients during the exposure is also required to provide the same level of protection as it is an extension of the secondary barrier. Leaded glass is able to provide this level of protection but requires special care. If you are curious about the thickness of the glass in the window, typically 4 times the thickness of the glass is needed to be that of the lead. So if 1/32 of an inch is required for the lead, 4 times that would be 1/8 of an inch. One fact to point out is that the primary beam must be scattered at least twice before reaching the operator. This means that the radiation energy will be so minimal that it is unlikely to cause any damage. This is because each time the X-ray photon scatters, it is 1/1000th of the original intensity. Other considerations in building a room are required at the seams of the lead in the wall, especially at the corners. All joints must have a 1 centimeter overlap or double the lead thickness, whichever is greater. Rooms must be inspected and tested prior to use, and the corners are tested to ensure leakage radiation is not exceeding the limit. We should take a moment and also discuss the ceilings and floors of a radiography room. The ceiling is a secondary barrier and would follow the same requirements as the control area wall. The floor, on the other hand, is considered a primary barrier and requires the same level of radiation protection as the wall behind the upright bucky. Oftentimes in industrial buildings, the floor is made of concrete, and it has been determined that 4 inches of solid concrete is the equivalent of 1.5 millimeters or 1/16 of an inch of lead. These barrier thicknesses that I just reviewed are the minimum, and sometimes more protection may be required. To determine the amount of radiation protection that is needed, we use an equation. The equation takes into consideration a number of factors, including workload or how many exams and at what radiation dose. This is calculated as the MA per minutes. This is multiplied by a use factor, which is multiplied by an occupancy factor, which is the amount the adjacent rooms are occupied throughout the day. This is then multiplied by the maximum kVp. The D in this equation is the average distance from the tube to the wall or barrier. This isn't an equation that an average technologist will need to figure out, but it is good to know that these factors are considered when determining the amount of lead necessary for an energized X-ray room. Note that the lead required is proportional to the workload, usage, adjacent occupancy, and kilovoltage capability of the room and is inversely proportional to the distance between the tube and the walls or barriers. Related to the adjacent occupancy concept that we just reviewed is the type of radiation areas and the regulations required for each. The barriers we just discussed are to ensure that the minimum requirements are met. Controlled areas are those that are mostly occupied by radiation workers. Because we as radiation workers are properly monitored for occupational exposure, there is less strict rules, and the limit of radiation for these areas is not to exceed 100 milliroentgen per week. An example of a controlled area is the technologist work area. Uncontrolled areas have even more strict limits and can only receive 10 milliroentgen per week, since these are the areas where the general public has access to. This includes waiting rooms, hallways, and where non-radiation workers would spend their working day, such as the radiology secretary's desk. We talked about the regulations for constructing a room that contains equipment that produces ionizing radiation. So now let's talk about the regulations related to the equipment itself. We will first start with fluoroscopy, since that is where the highest potential doses can be accumulated. The fluoro tower needs to have a minimum of 2 millimeters of lead. This lead is considered a primary radiation barrier since the primary beam is likely to interact with it. The fluoroscopic X-ray tube must not be able to produce X-rays while the fluoro tower is in the park position and not aligned with the tube underneath the table. The bucky slot cover reduces radiation to the lower abdomen and gonads. It must contain at least 0.25 millimeters of lead. the fluoro lead curtain must also have the same lead thickness of 0.25 millimeters. The X-ray room must be situated in a way that keeps the operator safe. As stated earlier, the X-ray tube cannot be directed at the control area where the control panel is located, and oftentimes the room is situated so that this would require a great deal of equipment manipulation to accomplish. Another requirement of X-ray equipment is that the X-ray tube housing must contain at least 2 millimeters of lead throughout the casing. This is to keep the leakage radiation to a maximum of 100 milliroentgen per hour, 1 meter from the X-ray tube. Many radiography units have other safety controls that are not required but help to keep the patient and technologist safe. For example, many systems have automatic collimation that closes the collimation shutters to match the size of the cassette that was placed into the bucky. Another safety feature is many systems will not allow the exposure switch to be activated if the tube is out of alignment with the bucky and not properly detented. The control panel of the radiographic room is regulated as well. The control panel must display the technical factors used. In addition, the cord for the control switch must be short enough so that the operator could not be outside of the control area when engaging the switch. In addition, the switch must be a dead man switch, meaning that the switch must have pressure applied to engage, and when the pressure is released, the exposure terminates. This prevents someone from letting go of the switch and the exposure continuing. All X-ray units must have an audible or visual signal that the exposure is engaged. Most systems that I've worked on utilize both an audible and visual cue. Now I know I just mentioned that the cord for the control switch must be short enough so the operator cannot leave the control area while exposing the patient, but I just wanted to quickly remind you that the mobile X-ray unit's cord must be a minimum of 6 feet so that the technologist can use distance to their advantage. Signage is important to ensure radiation protection of the general public that could wander into a room where a procedure using radiation is being conducted. A sign stating "Caution, Radiation Area" is required to alert people of exposures reaching over 100 milliroentgen within 5 days or 5 milliroentgens per hour. In areas where 100 milliroentgen per hour can be reached, the sign must state "Caution, High Radiation Area." We discussed numerous regulations and parameters that are required for the radiation safety of ourselves, colleagues, and the general public. It is good to know where we obtain the information that has guided those making the guidelines and regulations, and we should know who enforces them. We will first review organizations that provide data and recommendations about radiation protection practices. The National Council on Radiation Protection and Measurements, or the NCRP, as well as the International Council on Radiation Protection, or the ICRP, provides loads of information about radiation exposure, dose, and protection recommendations. Just about any search on radiation protection will lead you to these two organizations. The same goes for the National Research Council, which is part of the National Academies of Science, Engineering, and Medicine. More specific to us as technologists, the ASRT, or American Society of Radiologic Technologists, has a vast body of publications and recommendations of best practices in our field to guide technologists in ensuring the safest of working environments. Another society that has contributed greatly to the recommendation of safe radiation and magnetic resonance imaging practices is the American College of Radiology, or ACR. So now that we know who is contributing to the body of information and the current recommendations, let's discuss the agencies that enforce regulations related to radiation. One thing to note is that there are recommendations and there are regulations or guidelines. Typically, only the regulations or guidelines are enforced. Recommendations are encouraged and can affect reimbursement or accreditation. So often the recommendations and regulations are treated the same because not being in compliance with either will cause problems for an organization. What I want to review now are the agencies that enforce regulations. Facilities can be fined or shut down if not in compliance. The first one I'd like to review is the Nuclear Regulatory Commission, or NRC, and this regulatory agency publishes minimum standards of radiation protection. In the United States, each state has an option to be an agreement state or a non-agreement state. States can opt to be an agreement state and determine their own guidelines and enforce those guidelines. However, they must meet the minimum guidelines set by the federal regulations in place. Most states have opted to be agreement states with the NRC. A non-agreement state is one that chooses to follow the federal regulations. The Environmental Protection Agency, or EPA, monitors radiation exposures of the general population and sets guidelines and limits to protect our health. The Food and Drug Administration is an unlikely regulatory agency for radiation protection. However, the FDA regulates radiation-emitting products through their subdivision, the Center for Devices and Radiological Health. You are probably all familiar with OSHA, which stands for the Occupational Safety and Health Administration. This federal regulatory agency provides guidelines for employers in order to keep radiation workers safe. The last two regulatory agencies that I want to cover are state agencies. Each state is different, and as a result, I'm not able to make a blanket statement that will apply to all states, but many state departments or health agencies enforce radiation protection guidelines. Inspections can be a result of a complaint. State licensure organizations may also impose discipline for technologists that violate radiation protection standards. I hope you have found this series of videos interesting and have gained valuable knowledge to protect yourself and others when practicing as a radiologic technologist.